Hi there. Today we're going to look at section 2.5, which is the chain rule. So let's jump in and get started here. So the rules we've seen so far cover sums, difference, constant multiples, and products and quotients. But this is something a little bit different. A lot of the functions we're going to see in this class are composite functions, where it's a function essentially sitting inside another function, if you want to think of it that way. And so when we define a composite function, so here you can see that I've just defined it. There's lots of ways to define it. This is just the way we do it in calculus. That you have a g of x function sitting inside of an f of x function. That the product is actually given by this formula called the chain rule. And it doesn't look like what you would expect to see. The proof of this chain rule is at the end of the slides. You are not required to know this proof, but I did put it in there, so I'm not going to go over it. Even though if you are interested in finding out why this formula is true, it's in the notes for you guys. But I'm not going to be doing it in the video. So the idea here is that if we have capital F of x is f of g of x, so that's how it's read. You can say f composed with g or f of g of x. That the derivative is f prime of x, so capital F prime of x is f prime of g of x times g prime of x. And then this is one way to write it. The other way to write it is the Leibniz notation, where it's written as, so here we have dy dx is dy du and du dx. Because we're defining this g of x as another function called u. So it's sort of like this is the derivative of y with respect to u, so that's the outside function. So this is the way you want to remember the chain rule. You will use the chain rule probably every day of calculus. For those of you moving on to Calc 2, multivariable, and differential equations, you will use the chain rule every day of all of those classes. So the easiest way to remember this is it's the derivative of the outside function times the derivative of the inside function. So if the outside function is like our f of x, or f of u, using the Leibniz notation, right, f of u, the inside function is g of x. If you look at the formula, it kind of makes sense here, right? It's the derivative of the outside, and then notice that the inside function doesn't change. But then we multiply by the derivative of the inside function. So we're going to use this rule. It's the only rule we're going to use in this section. Some of the other sections we've seen 4 or 5 different rules. One rule today, because we're going to use it a whole bunch. So let's jump right in and find the derivative of this function that I called h of x. It's cosine of x squared. So you can see clearly that it's two different functions, right? It's not a simple product, a difference, a constant multiple, or a quotient. It's nothing like that. It's a function sitting inside another function. So what we want to do is write the function as f of g of x, and then identify the pieces. So the outside function here is f of u, which is just cosine of u. And the inside function, you can call it u or g of x, doesn't make any difference, is x squared. So the idea is that we've taken the x squared out of the cosine. And we actually have to deal with it separately. That's what the formula says. So we always do the outside function first, right? So we're just going to plug everything into the chain rule. So we do f prime of u first. Notice that that's the outside function, right? We're doing that one first. So the derivative, so remember it's dy du, or if you just want to use prime notation, that's fine too. Don't call it dy dx or df dx, because it's not. This is a function of u, okay? So the derivative of cosine of u is, of course, negative sine of u. Then what you do is you plug g of x back in, so it's negative sine of x squared. You don't have to show all of this work every time, but for the first example, I'm breaking it all the way down just to show you how it works. So that's the derivative of the outside function. So look at what we've done here. If we're taking the derivative of this, notice the x squared stays the same, and this cosine turns into a negative sign. But the chain rule says we have to multiply by the derivative of the inside, so we do that next. So g prime of x, well, that's the derivative of x squared, that's just 2x. And then we plug everything into the formula. So h prime of x is f prime of g of x, which we've already found to be this, times g prime of x, which is 2x. And again, you can leave it, you can leave it like that. In terms of simplification, not a huge deal if you simplify or not. Don't spend a lot of time doing extra simplifications in Calc 1. Maybe future classes that'll be required of you. Calc 1, not so much. So notice that it's kind of hard to see where this answer comes from just from the original problem. Some of you have taken Calc 1 before, so you know what I'm getting at. That later on, you end up seeing a lot of the same sorts of chain rule over and over and over again, and you kind of get the hang of it a little bit. So look here, outside function, negative sign. G of x stays the same. Derivative of the inside function is 2x. So you really don't have to show a lot of work for the chain rule. In fact, as we progress through the slides today, I'm going to show less and less work every time. All right. So you can combine this chain rule with other rules, of course. And we saw that in earlier sections where we combined lots of rules together. So you can combine the chain rule and the power rule. Right? So if you're using that u idea, remember u is just any function, then you get the power rule times the derivative of the inside with respect to x. So this is just a combination power rule chain rule. Or if you want to write it like this, if you have a function to a power, right? Look, the power rule is in effect, so the n comes down, lower the power by 1, multiply by the derivative of the inside. So let's actually see, well, there's two more ways to combine rules, and then we're going to see an example that uses all of these combinations. Also, we can extend the chain rule to include any number of functions. This doesn't come up a ton, but it does come up in physics, biology, chemistry, economics. You guys will, no matter where you go, if you're taking more advanced math, you will see this. So here we have f of g of h of x. So it's a chain rule inside a chain rule. You have to do the outermost derivative, leave the two inner ones alone, multiply by the middle derivative, leave the middle one, then leave the inside one alone, and then multiply by the most inside derivative. So we're not going to prove this because this proof is similar to the proof of the chain rule. But it should make sense. Don't memorize this formula. You'll see that there's a sequence to solving these. All right, let's jump in. We're going to do all of these. So these are pretty typical problems. So we're just going to go through these in order. I'm going to show you how much work I recommend that you show. Just remember, every time you skip a step, there's a chance you might make a mistake and not catch it. So you don't have to show every little tiny bit of arithmetic and algebra, but you should show all the calculus. All right, let's look at the first one here. So the derivative is just the derivative of this whole thing. Now what we're going to do is rewrite this sine to the fourth, as sine of x to the fourth. Now, those are logically equivalent. Okay, these two things mean the same thing. This thing here means the same thing as this. But it's hard to see what the inside function is here. Remember, we're going to need the chain rule. So when you write it like this, it's much easier to see that our sine of x is the chain rule. That's our inside function, right? And the u to the fourth is going to be our outside function. Over here, it's a lot easier to see what the inside function is, right? The x to the fourth is our inside. and the sine is the outside. So we just rewrite it using the notation that makes it easier to read. Now we're going to use the sum rule for derivatives. I'm distributing the d dx inside the brackets. You don't have to do this. We know that the sum rule is there, so it's not like a required step. But there are different inside functions, which means you're going to use the chain rule twice. Once for the first bit and once for the second bit. If you just write it like this, you might forget to use the chain rule twice. Okay, so when you do it like this, you're sort of reminding yourself, hey, that chain rule is going to pop up twice. Make sure we use it twice. It's just another way to sort of get into some good algebra habits so that you guys don't mess up. Well, I mean, look, you're going to mess up. We all mess up, right? But the idea is, can you catch the mistake without going back and starting the problem over? That's your goal. All right, so first thing you do is you evaluate your outside derivatives, right? So here, the outside function is u to the fourth, right? And again, I'm skipping the u step. We know what it's going to look like. I'm going to back up and show you on a previous slide. We know what it's going to look like, right? We know that we have a function to the nth power. So we know that when we take the derivative, the n is going to come out front, the inside function is going to stay the same, and the power is going to drop by 1, and then we're going to multiply by the derivative of the inside. That's all I'm doing here, okay? I'm just bringing the 4 to the front. 4 minus 1 is 3, keeping sine x the same. Now the chain rule says I have to multiply by the derivative of the inside, so I'm not going to do that yet. Remember, you can have chain rule, inside chain rule, inside chain rule, or sometimes the inside derivative is very complicated. Just no reason to be in a big hurry. Just delay that step one extra sec, just delay it. Because if you make a mistake and you're skipping steps, you won't catch it. If you make a mistake while you're showing the steps, you'll find it. So here, the outside derivative is just going to be, so here we just have sine of x to the fourth. So the inside function stays the same. The outside function, derivative of sine is cosine. Multiply by the derivative of the inside. Now we're going to do our inside derivatives. So all I did is delayed an extra step. And I know what you guys are thinking. You're thinking, look, I know the derivative of sine is cosine. Couldn't I just write it here? Or I know the derivative of x to the fourth is 4x cubed. Couldn't I just write it? Couldn't I have just written it here? Well, sure. But if these are more complicated and you haven't worked out the habits, you're going to skip a step and you're going to get the answer wrong and you're going to spend a half hour trying to figure it out and you won't be able to figure it out. Take the extra 12 seconds, do the little bit of extra work, and get the problem right the first time. Well, it turns out that's the end of the problem, right? I rearranged it a little bit just to clean it up a little bit. It's sort of a good habit to get into to keep all of your polynomials in front of cosines. Keep cosines on the far and sines on the far right, just so you don't accidentally think that the parentheses here is multiplication. Because you might look at this and forget and think, oh, x to the fourth times 4x cubed. You don't, I mean, it's not that, but you might step away from the problem and come back and forget what was going on and be tempted to try to multiply this out. So if you pull that 4x cubed to the front, it's generally a little cleaner looking and you're not tempted to kind of make unnecessary algebra mistakes. So there you go. So that's the answer. And looking at the original problem, it's kind of hard to see where that comes from, right? You really got to take some time and kind of figure it out. So derivative of sine to the fourth is going to be sine cubed, right? Because the power is going to drop. The 4 comes to the front. The x stays x, right? But remember, x is not the inside function here. Sine of x is the inside function. So you need the derivative of the inside. And this one's a lot easier to see, the chain rule, right? It's cosine of x to the fourth, and then 4x cubed from the derivative of the inside. That's basically what we're going to be doing today. So we got 3 more examples, I think. And they all more or less look like this. They all follow the same steps. I highly recommend that you work on showing the work in a really nice way like this. All right, next one. So here we have f prime of t. So what I did here is I actually just rewrote this like this. because we don't know what to do with radicals when we take derivatives, right? This is going to be a quotient rule, right? It's a fraction. But we don't have a fraction rule. I'm sorry, we don't have a radical rule. You need exponents. Now, some of you also might be thinking, why don't we write that as a negative exponent? It turns out, anytime you have a fraction, the algebra is always easier using the quotient rule compared to the product rule, just so you know. And the algebra is half the battle in this class. All right, so there's our quotient rule, right? So here I'm using prime notation. So it's the low function times the derivative of the high function minus the high function times the derivative of the low, all over the low function squared. Notice I'm not evaluating any of these derivatives yet. I'm not simplifying. I'm just filling in the quotient rule. Now we're going to take derivatives and use the chain rule for the outside function. So the chain rule didn't happen yet because we didn't have any derivatives yet. Now we have derivatives. So the derivative of t is just 1, so that doesn't do, there's no chain rule or anything there. But I need a chain rule here, right? So I have to do the derivative of the outside function first, and then I have to do the derivative of the inside function. So the outside function is this u to the 1/2, so we bring the 1/2 out, drop the power by 1. Inside function stays the same. Then we take the derivative of the inside, right? 2 minus t squared, derivative. And then I squared the denominator, right? So you can see that I'm kind of, like all the easy steps, easy derivatives like this, cleaning up, like cleaning up this mess here. You don't want to have a 1/2 and then a square. Ugh, that's horrible. You don't want that sitting down there. Go ahead and just kind of clean up the algebra as you go, but don't get ahead on these derivatives. Even if you can do it in your head, it doesn't mean you should. Now we do the inside chain rule. I simplified this 1, right? Anything times 1 is itself, so that just went away. This 1 just goes away. And then I just went ahead and did this derivative. That's the only other thing left. And you can leave it like that. So this is what it looks like unsimplified. But this actually simplifies really nice if you take the time, and if you want to simplify it, you can. So then it becomes one of those things, it just depends on what you're doing with the problem. If it's a test, just leave it like this. There's no reason to use extra time simplifying. But on a homework, maybe you don't want to type all this in. Maybe it's easier to type this in. Well, sure, go ahead and simplify it. Or maybe, you know, the question will say, find where this function has a vertical tangent. And you need to set this denominator equal to 0. Well, here, there's division by 0 up here, right? We have a negative 1/2 exponent. So maybe the algebra is easy here if you need to do more things. We're going to see some problems later on, next couple sections, that kind of look like this, that it is in your best interest to simplify, but it's not required. But it's good algebra practice for sure. Make sure you can get from here to here if you're worried that you can't, okay? But on a test, this is fine. Next one, cosine of cosine of cosine of x. You might think, well, that's a silly function. Maybe it is. Let's take the derivative and see what happens. So we take the derivative of the outside function first, right? So the inside function here is really two inside functions, right? The inside function here is really cosine of cosine of x. So the chain rule says, take the derivative of the outside, right? So cosine is negative, sine. Everything inside that outermost function stays the same, times the derivative of the inside. Now, do you want to do this in your head? Not necessarily. Just delay it one extra step and do that step here. So this stays the same. Here we do the derivative of this. Derivative of the outside function is sine. Inside function stays the same. And then we just have to do the derivative of this most inside function. And we've done all the derivatives, and you really just want to clean it up a little bit and simplify. So we got 3 negatives here, and those all simplify to a single negative. So you really want to do stuff like that. Again, on an exam, you could leave it like this first one. Totally fine. But maybe for the homework and stuff, you just want to clean it up a little bit, make it easier to enter in, or whatever. Okay, last one is even more chain rule. Nothing fancy going on here. This is just a variation. You guys have seen problems like this on the homework. I wanted to do this one because chain rule is brand new, just to show you how it works. So if we have a function h of x, and it's square root of 4 plus 3f of x. So you can see that f of x is just some inside function. And let's say we know f of 1 is 7. We know f prime of 1 is 4. Can we find h prime of 1? So it turns out that if you know the function and its derivative at a point, even if you don't know what the function is, this composite function, you can find its derivative. Okay, so as we've done before, you just want to take the derivative, right? And first thing we do is rewrite it, of course. Right? We want to put that fractional exponent in there. Then you just take the derivative. So power rule, bring the 1/2 to the front, lower the power by 1, times the derivative of the inside. So this is all just chain rule. It's the only rule we're using here. Then you take the derivative of the inside. Right? And if you forgot, I'm not showing steps that we've covered before, right? We know the derivative of 4 is 0, so I don't even have to show it. You don't have to write that on the test. Anytime you see a plus a constant, you don't write the derivative. There's nothing to write. If it's times a constant, well, yeah, sure, of course. It sticks around because of our constant multiple rule for derivatives. Then what I do is I simplified the answer. If this were the whole question just to stop here, you could have stopped there. But the question says, look at what it says. If I know these two values, find this value. Which means I'm going to have to plug some numbers in. I'd much rather plug them into this than this. And it's just easier. So I went ahead and simplified just to make the arithmetic easier. Now we have to find h prime of 1. So that means that every value, f of x or f prime of x, becomes f of 1 or f prime of 1. And I actually know what f of 1 and f prime of 1 are. Right? Those were given on the previous slide. Plug them in, and you get 6/5. So nothing fancy happening here. And that's it. So the homework looks a lot like one of the things we've done. I didn't have time to go over every type of problem. Give it your honest effort. You only have to get 90% of the questions correct to get 100% on the homework if you get it done 24 hours in advance, right? So get a jump on this. Don't wait. And as always, if you have questions, let me know. There's lots of practice problems here in the ebook or in the textbook, depending on what you have. Definitely check this stuff out. Get as much practice as you can with the chain rule because it is very important and comes back over and over and over again. And you guys can check that out. Here's the proof of the chain rule. I'm not going over it, but it is at the end of the slides. So if you guys have any questions, you can email me or post questions on the discussion forum. And that's it for today. And I'll see you guys next video. Bye-bye now.